Welcome back to this lectures on linear algebra. Last time we have been discussing some examples of a dimension of a vector space. I will continue this at least half of this lecture to discuss more examples on the dimensions. So let us if let V be a C vector space. C is the field of complex numbers. Then we know that V is also R vector space by a restriction of scalars. Moreover, V is finite dimensional over C if and only if V is finite dimensional over R. In fact, from a basis of V over C, we can also write down a basis of C over R. So, moreover, if Vj, J in J is a C basis of V, then take these vectors Vj and also take I times Vj, where I is the imaginary complex number which is a square root of -1, or better would be say whose square is -1. Then Vj along with I times Vj, they form an R basis of V. So therefore, dimension of V as a R vector space is 2 times dimension of V as a C vector space. That is twice. This we can do it actually more generally. More generally, if L over K is a field extension of finite degree, and the degree of a field extension is by definition dimension of a bigger field over a smaller field. If this is M, which is finite, and if V is an L vector space, with basis, with finite basis Vi, I in I, then V is also K vector space of finite dimension, and the dimension as a K vector space, dimension of V as a K vector space is M times dimension of V as a L vector space. This is very simple. Again, what you do is you take a basis of L over K and multiply each basis element by this basis, and put together they will generate V as a K vector space. So I will just write it down. In fact, if alpha 1 to alpha m in L is a k basis of L, then alpha I times Vj j in j, I is varying from 1 to m, is a k basis of V. This is the same proof as real case. Okay, so however these arguments do not work for a particular field extension Q over R, R over Q. R over Q is also field extension. But not finite. In fact, not even countable. Countable dimensional. In view of this, studying vector spaces over Q is much more intricate than studying real vector spaces or complex vector spaces. Okay, the next example. If you have a field K, then we have seen the polynomial set of polynomials, the set of all polynomials with coefficients in K is a K vector space. And by definition of polynomials, 1 x, x square, x power n and so on as n varies in natural numbers form a k basis of kx. Therefore, dimension of kx as a k vector space is cardinality n, which is aleph naught. It is a countable dimensional vector space. If I fix for a fix n natural number, if I restrict myself to the polynomials of degree strictly less than n, so these are all the polynomials f with degree of f strictly less than n, then this is clearly a k vector space. This is a k vector space which is a subspace of the vector space of polynomials and 1 x power n minus 1 is a k basis of kxn. That means dimension kxn over k is precisely n. All right. Okay, now next is if you know basis of a vector spaces and if you take their direct sum or direct product, then you get a basis for the direct product vector space. So, this is the next example. So, let us do it for two vector spaces first. V and W be two k vector spaces with basis k basis vi, I in I, and wj, j in j respectively. Then as we have seen in earlier lecture, the V direct sum W, this is the product set with the component wise vector space structure, is a k vector space with k basis. You put 0, first is Vi in the first component, then 0 I in I, and 0 Wj, j in j. To check it is a basis, we need to check that it is a generating system and linearly independence, but that is almost clear from the definitions, because the vector space structure on the product set is component wise. So one has to check that this is a generating system and linearly independent. That I leave it that checking for you. So in particular what we get is, we get a dimension formula, that is dimension of the direct sum equal to dimension V plus dimension W. This is dimension formula, and nothing special about two vector spaces, one can do it for finitely many. So let me just mention, if V1 to Vn k vector spaces, then dimension of the direct sum V1 direct sum Vn is summation I is from 1 to n dimension kVi. Note that this direct sum we cannot, I want to not talk more about this now, infinite case now. When I have enough machinery, I will discuss more about that. Okay, now one more example. This example is useful for engineers. Only the differential equation, solutions of the differential equations. So let P be a monic polynomial with coefficients in either real numbers or complex numbers. Be a monic polynomial of degree n, and k is either C, field of complex numbers, or field of real numbers. And what we are looking is the differential equation, consider the linear differential equation with constant coefficients. PD y equal to 0, homogeneous. Where d is the differential operator d by dx. and we are looking for functions. So what are we looking for? Solution space is precisely all those functions y which are functions in from k to k, and also k y should be n times differentiable, and it should satisfy this equation PD y is 0. So let me call the solution space as V. First of all, note that this V is a k vector space. This is immediate from the fact that the differentiation is a linear map. The differentiation respects addition and also respects the scalar multiplication. So it is a k vector space, and actually one can write down explicit basis for this vector space. That is what I am going to do. To write basis of V, what we need to do is you look at this polynomial P, and this is definitely either real or complex coefficient polynomial, but over complex numbers definitely it will split into linear factors, because C is the field of complex numbers and we know it is algebraically closed field. Therefore, every polynomial splits into linear factors. So this polynomial will look like x minus lambda 1 power n1, x minus lambda 2 power n2, x minus lambda r power nr, where this lambda 1 to lambda r are complex numbers. Some of them could be real complex numbers, and these n1 to nr are natural numbers, non-zero natural numbers. They are precisely the multiplicities. So ni is a multiplicity n is the multiplicity of lambda I, or I is 1 to r. In terms of these lambda i's and in terms of the ni's, we are going to write down a basis of V, and in that, and then we will know what is the dimension of this vector space. We will explicitly know how many linearly independent solutions are there. All right. So then the quasi polynomial, these functions which below I will write down, they are called quasi polynomials. What are they? Start with the exponential e power lambda 1 t. This is exponential function. Then t times e power lambda 1 t. Go on till t power n1 minus 1 times e power lambda 1 t. Then start with lambda 2 e power lambda 2 t, t e power lambda 2 t. Go on till t power n2 minus 1 e power lambda 2 t, and then keep doing this for all lambdas. So e power lambda r t, t e power lambda r t, last one is t power nr minus 1 e power lambda r t. So this is a block, each root will give you this block. There are blocks. These quasi polynomials form a C basis of the solution space V. This is very easy to check. We have, in fact, we have checked in earlier lectures that these functions are linearly independent, and they generate is a typical theorem one proves in an analysis course. So I will not prove it here, but maybe I will write the proof in supplements. Okay, so in particular the dimension. So see supplements. In particular, the dimension is the cardinality of a basis. Dimension of a solution space is therefore n1 plus n2 plus nr, but this is nothing but the degree of phi n equal to degree of p. So, what we have noted is the solution space of a linear differential equation with constant coefficient equal to the degree of the polynomial. That is the assertion. Okay. So, now I want to give couple of remarks about how do we minimize our checking to check somebody the basis of vector space or not. Because to check it is the basis of a vector space, we need to check two things. One is the generating system and the other is the linear independence. So, somehow if you know earlier or by some other means that the dimension is known, then how do you decide given vectors form a basis or not. So, this is precisely the content of the next theorem. Theorem says, so let V be a vector space and V be a vector space of dimension n. And let V1 to Vn are n vectors given in V. Then the following are equivalent. 1 V1 to Vn is a basis, two V1 to Vn is a generating system, for V, and 3 V1 to Vn are linearly independent over K. So, this theorem says if you know that they are correct in number, then you only have to either check generating system or linearly independent, then it will automatically be a basis. For example, the proof is very easy, I just want to indicate orally. So, proof 1 implies 2 and 1 implies 3, they are trivial because basis should be generating system also and basis also should be linearly independent by definition. So, to prove, for example, 2 implies 1, that means it is a generating system you have given and the number is correct, then we want to prove it is a basis. But just note that we have noted earlier, given any generating system, by throwing away the unnecessary elements we can arrive at a minimal generating system, and minimal generating system is a basis, that is what we have proved earlier. So, if at all a generating system is not a basis, then we can cut down, but that is not possible in this case because then we will get a basis who has fewer elements. But we have checked yesterday in last lecture that any two bases have the same number of elements, so that is not possible. Similarly, for the linear independence. So, check that, I will just mention here, check that 2 implies 1 and 3 implies 1. Okay. Also, I would like to mention one more theorem like this, which is very useful sometimes to check to compute dimension exactly. So, that is the next one, whose proof also I will omit because it is similar to the theorem we have just mentioned. So, let V be a k vector space and n is a given natural number, then first statement, V is finite dimensional of dimension less equal to n if and only if every n plus 1 vectors in V are linearly dependent. This is because we know if you have a basis consisting of n elements less equal to n elements, and if you take any n plus 1 vectors, they cannot be linearly independent, because if they were linearly independent, then we could extend it to a basis of V by exchange theorem, but then the dimension of V will be more than n plus 1, bigger equal to n plus 1, that is not possible. So, that is similarly we can write down equality here. So, V is finite dimensional of dimension n if and only if, of course, this part will be same, every n plus 1 vectors in V are linearly dependent and there exist n linearly independent vectors. In V. So, the proof is similar to that of 1. Now, these are the statements about linear independence and the dimension. Now, similarly, I will write down two analogous statements which will involve generating systems. So, third, V is finite dimensional of dimension less equal to 1 or less equal to n if and only if V has a generating system consisting of n vectors. If it has a generating system consisting of n vectors, then by cutting down we may get dimension smaller equal to. One more and then we will make a break. Again, V is finite dimensional of dimension equal to n if and only if of course V has a generating system with n vectors and every generating system has at least n vectors. That means every generating system should have more bigger equal to n vectors. So, we will stop for a break and we will continue soon. Thank you.